composition at this point? If I could just separate the dye elements at this point, I'd be happy.
Okay, thank you, James, and we will continue with the last speaker of this session, and it will be Rafael Piestun, and he will be talking about 3D modulated optical crystals as computer-generated volume holograms.
You forgot to confirm it.
I'm sorry. Oh, yeah, you can go back and you can listen to me drink coffee for the rest of the
Okay, good morning. Today I'm going to talk about a topic that is somehow related, but mostly unrelated to what we've been seeing this morning. Holograms have existed for 60 years now, and we know in learning basic courses that the hologram can generate arbitrary wavefronts, and what we learn is that to generate a hologram, we use coherent light, interference at a reference wave, and an object wave, and then through a process of development of a film, we can get any wavefront, the full 3D information. Now, in the 60s, late 60s, Adolf Lohmann invented what is called a computer-generated hologram. That was very difficult at that time because the computers were very, they didn't have much power. So they mostly did very simple calculations. But that field developed in the 70s and 80s and gave origin to the topic of diffractive optics. And today, in these days, we've seen how computer-generated holograms are used for optical tweezers, which has become maybe the most common application of computer-generated holograms. Now, the main point of computer-generated holography is that you can generate things, wavefronts that don't exist in nature. Or if you optically record a hologram, you can only record things that already exist. With a computer-generated hologram, you can generate something new, and we've seen vortex beams and Gauss Laguerre beams and all kinds of interesting things. So the question is, what can we do new in holography, given that it's been around for 60 years? So I think I have a point here. Let's look at a simple classification of holograms. We can see that thin holographic optical elements is what essentially derived from the discoveries of Vita and Kupatnieks in the 60s, which are optically recorded holograms. And those are originally were thin holograms. Later on, people discovered the volume holograms, which can encode more information, have some nice properties, more efficiency. You can have also multiplexing and other functions. So volume holograms were developed, and then here I have the computer-generated and diffractive optics. But as you can see, that there is a box there that wasn't filled. And the main reason is that, for one, the computation of these holograms is pretty heavy computational, and from another point of view, it's very hard to fabricate this. But I think this is the point where you might become interested, because you know that there are several companies where you can buy specialized modulators made of liquid crystals to make this type of holograms. There's no company that is selling these holograms because these holograms were not developed. So what I'm going to talk today is about this type of holograms, okay? And this could be a motivation to develop liquid crystal arrays in 3 dimensions that could generate these new functions. Okay, let me go through this just a bit. This is related to the generation of light fields inside a volume, and we've published in the past some papers on this. Essentially, I believe this is the first paper that generated arbitrary, or as much as it's possible, arbitrary functions inside the volume. But today I'm going to talk about this part of the problem, which is volume optics that can control frequency, space, and polarization properties of light. And this involves some problems in terms of analytical statement of the problem and some experimental methods which are complicated, and we are going to show the first results in these areas. Now, this is what could be categorized or classified as something like volume optics, which is, I believe, is the next frontier, where you're trying to make optical systems inside the volume with arbitrary changes of refractive index and polarization. So, as opposed to classical optics, where we have essentially planar devices, here we're talking about making volume systems, okay, with a continuous change in 3 dimensions. So we know that periodic structures exist and can be fabricated with very fine accuracy, and that's a whole topic of photonic crystal. We've seen some very, very interesting talks here this week. Even in our group, we have developed some new techniques to fabricate this periodic photonic crystal. Now, periodicity is very interesting, but the question is that the point is that most of the interesting things happen when you break the periodicity. If you introduce a defect in a photonic crystal, you introduce a waveguide by generating a line of defects, or what will happen if we have an arbitrary aperiodic 3-dimensional structure. And that's what I call here a computer-generated volume hologram. So we could discuss what would be the appropriate name, but given my background, I call these holograms. And in general, I said any arbitrary 3-dimensional index modulation is computer design for some optical function. And as in the same way as computer-generated holograms, you can have absorption or phase modulation. So the index can be complex in general. And in general, this is aperiodic functions. So that's our goal. Now, the fact that we can do it doesn't mean we should do it, but there are some interesting applications, and that's why we are doing that. In fact, we talk about that we can have higher efficiency with volume computer-generated holograms than we can have with planar holograms. We can also generate new functionalities by multiplexing in angle or in frequency. We can also have additional degrees of freedom to shape a pulse, for example, in space and time. If you have only a planar hologram, you cannot fully modulate the pulse. With a volume hologram, you have all the degrees of freedom you need to modulate in space and in time. Additional advantages of these holograms is that you can make them very localized by shaping inside the volume of the material. You can encode information also, because you are free to do any design in the computer. And you can integrate this with other free space or guided wave devices. So just as an example, this is the first type of hologram encoding for 2 dimensions that was proposed by Lohmann, and the idea is to have a 2-dimensional array of windows, and then each window can be slide right and left, and the phase. So each window is associated with one sample of the wavefront, and so we have an amplitude and phase. The phase is encoded, which is the most important part, is encoded by the shifts of these windows. Okay, by shifting the window, we encode the phase. And if we want to modulate the amplitude, you change for example, the size of the window. So this is nice, but one way of looking at this is a 2-dimensional crystal with modulated, where each side is modulated. That's another way of looking at this. So with this type of approach, you can generate any wavefront. Now, in 3 dimensions, we have more freedom, as I said. So you can shift the windows shown here, but we can also shift them in Z, and we can pack several of those windows. So now we have more degrees of freedom to shift both in X and Y and Z, in X and Y, and also in Z, and then stack several layers of this. So this is the first of such holograms we fabricated. So we have a femtosecond laser in our lab, so that's what we use to fabricate this. This is so we took a piece of glass microscope slide, and then by scanning a focus beam, you can modify the refractive index of the glass locally by a nonlinear process. I'm going to talk a bit more about that. So what this shows is a DIC microscope image of one of these layers, and then you see each dot here is shifted, so you see an aperiodic array, but there are 4 layers like this in this hologram. So that's the reconstruction and the simulation, which agree. And then in this work, what we show is that by stacking more layers, you can improve the efficiency, which is one of the goals we wanted to achieve with volume holography. And of course, in theory, we could do better than in practice, but we could still improve the efficiency significantly. The second experiment is the proof of angular selectivity. So this would be like a grating made with an amplitude, modulation. And here we have 4 layers. This is just one example, 4 layers. And as you see, each layer is aperiodic. There's no periodicity. And the more layers you have, you increase what we could call the free spectral range. So that is the distance between the orbitals. Now, these plots essentially show the angular selectivity as you change the angle of the incident beam, how you see a spot in the far field, and that spot is going to be disappear as you rotate your incident beam, and then disappear for longer angles if you have more layers. Now, the important thing is that we can increase the efficiency, and the efficiency is going to be higher than a volume hologram, which is an absorption volume hologram. Okay? So in this case, one interesting thing is that we show that this array of aperiodic gratings is better than the periodic counterpart, okay, for a given set of parameters, which is, I think, an interesting thought. The other thing we try to do is polarization selectivity, okay, and that's something you can achieve with liquid crystals. In this case, there is a regime by which, if you use a femtosecond laser in the micro joule per pulse regime at the high repetition rate, you can generate these nano gratings inside the glass. But this is a phenomenon that occurs through the interference of the short pulse and the plasma generated inside the glass. And these nano gratings have long range periodicity. So then we can fabricate, this is just one snapshot with the DIC, large arrays of micro gratings. Essentially, each micro grating acts like uses the effect of form birefringence. So essentially, we have a birefringent medium at the macro scale, and so we can generate millions of these micro wavelets. Okay? So this could be, I believe it's more than 10,000 micro wavelets. But the location and orientation of the principal axis of each of these micro wavelets is designed by the computer. So if we go to the, again, we use an arrangement similar to the previous one, but now we have the orientation of the principal axis or the gratings is either vertical or horizontal. And in the shifts of this, with the orientation of the principal axis, we encode the information. And I don't know if you could see it. but this is the reconstruction. This is the reconstruction in the far field. There we go. Sorry about that. Oh. Let's do this. There you see, what you see in that movie is the reconstruction, by rotating a polarizer. So it's the reconstruction is polarization sensitive. Okay, so this is the first demonstration of such holograms. So then the next challenge was to generate a full volume. So in this case we use volume scattering theory. So the idea is you have this volume, we want to generate some pattern in the far field, and with angular multiplexing functions, for example. So we use the Ewald sphere, which is essentially a Fourier transformation of the contrast here, which is the index of refraction, square minus 1. We make a Fourier transform, we get the Ewald sphere, and then we use k-space, and we can calculate this similar to what happens in X-ray diffraction with the crystal. But now the difference is that we don't know what we want to put here. So this is the analysis. Now we need to do the design of this volume. So we optimize this on a loop and try to match the index here so we can get this reconstruction. But on top of that, we have some constraints because the index cannot be arbitrary, so we have constraints on this optimization problem. And then one can come up with something like this, which is a volume which is aperiodic and looks pretty much like a mess, but eventually it's going to give you that reconstruction. And this is the first demonstration. So here I show simulations by using the volume diffraction and an independent method, so to show, which is spin propagation method, to show that they agree. And then this is the first demonstration. Here we show the reconstruction by using angular multiplexing. So what is going on in this movie is we are shining with one beam and then moving angularly, and we get different reconstructions. Okay, let's try it again. Okay, so you see the C, then you don't see anything, and then you see the U. Okay, and all that is included in that volume I showed you. So with that, I have a short time. I want to conclude by saying that the computer-generated volume programs combine the best attributes of classical diffractive optics and holography, while providing degrees of freedom from novel functionalities. And we show that we can increase the diffraction efficiency, we can control polarization and angular frequency selectivity. I didn't talk about frequency selectivity. You can also control the space and time shaping of pulses. In my view, volume optics is going to be the next challenge in optical devices, and this is just a first step in that direction. Let me acknowledge the support by the National Science Foundation and other sources, and prior members of our group. Thank you for your attention.
Thank you. We have time for several questions. Okay.
Oh, that was really interesting. And I had a question about what differentiates thin from thick in your mind. How many layers do you need? 2 layers, 3 layers, 5 layers, 100?
As you probably know, there's a gradual transition from thin to thick. For example, if you have as you go thicker and thicker, you can have higher control over the selectivity. So you can get better discrimination in wavelengths or angular discrimination. So it's not a sharp transition, but anything that has more than 1 layer, in my mind, is a volume model. Okay.
who has the next question?
Just let me add, if anyone knows how to make a volume SLM, please stop me.
Well, so if nobody has a...
No.
Ah, very good.
I mean, you could think of making multi-layer, pixelated from the crystal devices. What are the requirements to make something interesting?
Well,
right now you have planar. I mean, display type is, has planar two-dimensional SLMs and volume, writing volume holograms for data storage. You can think of making multi-layer, say devices where the pixelated layers are spaced by, let's say, 20 microns. What actually do you need to be useful and interesting?
If you can make these SLMs very well aligned and with known properties, and if you can stack, let's say, 4 of them, then you can start doing this type of thing. So you could do angular frequency multiplexing. So you could have modulated or real-time volume holograms, computer trained. Yes. Now, I didn't talk about the computation. That cube I show is 64 by 64. So it takes a long time to calculate. But we expect that computers are going to become better. When Lohmann made the first computer-trained holograms were calculated by hand, essentially, and drawn by hand, and then photoresist. So we could calculate, for those SLMs, we could calculate functions offline, but I believe that in the future we can do it in real time, like now we stand with the optical tweezers. So then you could control different, for example, different pattern arrays for different colors to control optical tweezers. That could be an application of that. Okay, so it's over.
One more question, if you want to.
I just have a question which is maybe sort of simple-minded. Is angular multiplexing, is it significantly harder to do in the volume holograms than in the flat ones, the 2D ones?
You cannot have angular selectivity with a 2D one.
You can't.
Zero. You take diffractive optical elements, you rotate the laser, and you get always the same pattern.
The same thing.
Yeah. It moves, but it's always the same. With this, you rotate your incident beam and you change the pattern. Yeah. So optical storage is another application.
Well, thank you, Rafael, and thanks to other speakers to this morning session. We will have a coffee break, and so this session is officially closed, and the next session will start in about 15 minutes.